is probably my favorite city to ever be in and visit. And my previous company was headquartered in New York, and I always loved it when I got to come and be there. So of course, I wish I was there in New York, where most of you are located. But I'm really happy to be here and to be able to talk to you all. And a lot of the times when I get to talk about the kind of work that I do and the kind of topics that I talk about. It's often with data scientists, data analysts, and less people who are really explicitly thinking about data visualization. And so I think this is a really interesting group of people to be able to talk about this topic and to be able to kind of take an interesting focus on the kind of work that I do, the kind of tools that I build, and to be able to present, to be able to have this discussion here. So thank you, Naomi. Yeah, like my name is Julia Silge, and I work for our studio. And in my day job, what I do most of the time is build these open source tools, the software for machine learning and modeling. And data visualization is a huge, important, and central piece of the machine learning process that we're like that, and that's what I want to focus on in this talk here. It is one of the key tools of communication that we use when we're speaking outward, when we are taking the work and we are moving outward with the our results. We're sharing. But what we're going to talk about today um, is a different aspect of how data visualization is used. Not so much its role as a communication tool, but instead how people use data visualization as a tool to make better modeling choices. How plotting, making charts, data visualization is a tool of the system designers and the operators themselves. There we go. Okay, so using visualization is this hugely important tool for everyone who works with data, not just people who build models and do machine learning. And a lot of what we're going to talk about today is true because data visualization is effective at surfacing information to human beings in our visual channel. I'm sure as you've had other speakers come and speak to, the technical details of how this works, how we use these different ways of these different channels to be able to surface different kinds of information. And when it comes to data, these different visual ways of showing people things when it comes to data, they form how we think about the work that we're doing, how we think about the data that we handle, the models that we're trying to build, how we understand the problems that we're trying to solve, the machine learning systems that we're working within, and how we decide. And I especially want to focus on data visualization as a support or an aid for decision making. Because building models or machine learning systems is this very complicated, involved task. And I want to frame the plots and graphs that we make in this framework, very similar to how Tamara Munzer does here from her really excellent book. So we use code, we use these computer-based systems to represent our data sets for a very specific purpose when we're building models. It's to help us as their practitioners to carry out our task more effectively. And the task that we're doing is to build models or machine learning systems. So thought of really broadly, we're trying to be more effective when we're building this model. We're building this machine learning system. So what does that mean? What does more effective mean when we're building a model or a machine learning system? This can have a couple of different meanings. This can mean more accurate. This can mean more practically appropriate to the problem that we are trying to solve. And this can mean more fair. And we're going to talk about a couple of these different ways that we can become more effective in our modeling and machine learning and how we use data visualization to do that here. So I work on an open source framework in R called Tidy Models. That is built for modeling and machine learning. And a lot of the examples that I am going to be showing today and use today use Tidy Models code. Some of the specific goals of Tidy Models are to provide a consistent and flexible framework for real-world modeling practitioners, whether they're someone who is just starting out with modeling or someone who's a very experienced machine learning practitioner. Another goal is to harmonize the heterogeneous interfaces that we have within R and to encourage good statistical practice in the design of this framework, of this system. So I'm really glad to get to show you a little bit of what I'm working on, what I build, what my teammates and I have been doing. But a lot of what we're going to talk about today isn't specific to Tidy Models, isn't specific to R. In fact, it is pretty broad. We are going to focus on these data visualization practices for real world folks that are engaged in building models. So let us start by asking this question. When do modeling practitioners build data visualizations? So asking this kind of question requires us to think about the process of model building and to build a mental model of model building, if you will. So I'd like to put this out there as a schematic of what might happen during a typical process of someone building a model, starting from when they first are exposed to the data for the very first time to having a working model. So the model process starts with exploratory data analysis, EDA. This is a systematic, iterative process of exploring data to investigate it. After this comes feature engineering. This is the task of taking our original variables and creating or transforming the original variables to a more useful feature for our model. And then after this comes model fitting and tuning. I've represented this with like a lot of little thin, skinny bars to emphasize that when we use best practices, we do this with resampled data sets. So we fit and tune and fit and tune and fit and tune. And typically when we are in the process of doing this, we don't do this with one model, but in fact, we have multiple models that we want to try out, because we don't know ahead of time typically what model is going to be the best model for any given data set. Instead, we need to empirically try different models and see which one is going to perform best for the problem space that we're working in. Notice that we're not, so the next thing there is model evaluation, where we measure how well a model performs. And we use some metric here that's appropriate to that specific kind of model and problem. We measure how the model is doing. So we've kind of gone through the process here of starting, doing EDA, getting through to model evaluation. But the process is not done there, because this process is iterative. We go back to some of these stages again. We take what we've learned from this, from the sort of the first round, and we go back and we do some EDA again, because the questions have arisen that we want to find the answers to. We do spend more time in feature engineering to be able to build more effective features. And then, we go back and we try, say, the two models that worked the best the first time and fit and tune them again before evaluating. Also notice something about this process, that the process is ending with some goal or output, either something like communicating the results to people who need to know about them, or deploying the model to some production system. I represented that with a pretty, skinny bar there, but picture that really as transitioning to a whole other set of tasks. So in this talk, we're going to constrain ourselves really to talking about the things before we transition to that other set of tasks. We're going to focus on this iterative process of building the model itself. So during this process, machine learning practitioners can, of course, make plots at any point during this, if they want to or need to. But I want to make the argument that there are two phases of this modeling process where practitioners use data visualization the most. The first of these is EDA. This is this iterative phase of investigation, question generation and refinement and exploring. And this is a phase that some people might say is like before modeling and machine learning, but we're going to see how the investigations and understanding that is gained during EDA have a huge impact on the models that we create in terms of their quality, their accuracy, the impact that they have. The second is model evaluation. So this is the part of the modeling process where a practitioner has trained probably multiple models and is assessing, is measuring, and is comparing how well they performed. So if you were able to, come and like look over the shoulder of someone building a model during the whole process, these two points would be when you would see someone creating the most data visualizations. And I believe that using plotting and charting in a really lavish way at these phases is a sign of a healthy machine learning or modeling process. The reason why is that these two phases of the modeling process are the points of most important human decisions. These are decisions where validation of them can be difficult, often because, we might describe them as being art, not science, and that is because they are full of trade-offs. Different priorities are having to be weighed, and, like we're having to choose one often at the expense of another. And so visualizations are used at these 2 points of important human decision as an aid and as a support to carry out this task more effectively. So let's dig a little deeper and learn a little more. And let's start with EDA, with exploratory data analysis. And let's start by asking this question: why are these plots built? At a very high level, these plots are built to understand the data. So when a practitioner starts out on a modeling project, understanding the data is one of these first substantive tasks being faced. And that is because there is about to be a whole bunch of decisions that need to be made. And these data visualizations during EDA let practitioners ask and then refine specific questions related to the modeling goals, like what kind of model is appropriate? And then this feeds into the feature engineering phase that we talked about before, and be able to make decisions about what kind of pre-processing is needed. And all these kinds of questions are ones that machine learning practitioners ask, refine, and answer by making plots during the EDA process. So let's finally take a look at what some of these plots actually look like. So some of these plots take the form of very familiar statistical graphics, like this scatter plot. So this plot uses a data set called the Palmer penguins. It's of penguins that have been observed in Antarctica near Palmer Station, and it maps each observation to a point on the plot with aesthetics like the positions, X and Y, size, and color, representing things that have been measured about these penguins. So exploratory graphics like this one are important for modeling or machine learning practitioners because, for starters, they help us as machine learning practitioners understand the type and amount and quality of data that we have available. And then going further beyond that, they visually highlight relationships in the data that we can use in feature engineering or modeling. So if we wanted to build a classification model to predict the species of the penguins or maybe the sex of the penguins based on the other measurements that we have about them, the relationships that we discover or highlight or uncover in these kind of graphs inform the steps that we take moving forward from here. Plots for EDA don't always look like the super classic statistical graphics. In some ways, this is also just a scatter plot, but the mapping is different. Like what's being mapped is different. It is, well, it is in fact a map. So this is showing a data set of trees in San Francisco. So that big empty area is Golden Gate Park. And some of those other smaller empty areas are some of the smaller parks. And right away, we learned something here, right? Like the trees in the parks are not in this data set. And the color is mapped to who is in charge of maintaining each tree. Is it maintained by the Department of Public Works, or is it maintained by someone else? So if our goal is to train a model to predict who maintains the tree, the maintainer of the tree, a plot like this one is hugely informative and helpful for the practitioner, the person creating the model, in terms of what kind of model might we want to try? What predictors do we expect to be important? Like, do we expect spatial information to be important? And we use visualization as this tool in our process right away. So machine learning practitioners use visualization during EDA to make many different kinds of plots. So it's important that the tools we use during this phase facilitate fluent iteration through lots and lots of kinds of graphs. I have decades of experience with various kinds of scientific plotting tools. And my opinion is that learning about and internalizing the concept of the grammar of graphics is a huge step forward in this ability to efficiently iterate. Adopting a system that applies this grammar gets you this huge step forward in efficiently asking, refining, and answering questions to get ready to train models. So just like being able to have the ability to use a grammar in a language lets us put together sentences. Being able to fluently use a grammar for visualization lets us fluently do the kind of efficient iteration in EDA that you have to be able to do to get ready to train models. I'm a user of ggplot2, perhaps the best known system that implements the grammar of graphics. And the plots that I'm showing you here in this talk today are made with ggplot2 in the course of training models. And then they are used, like I said, to immediately answer questions that need to be for modeling. One of the first ones is what kind of model is appropriate? So let's say we start with a very straightforward data set and a very straightforward model. Say something like linear regression using ordinary least squares. So in tidy models, we have a goal. One of our big goals, one of the motivating goals behind tidy models is to harmonize the heterogeneous interfaces that exist in are in, what we might call the wild west of R's modeling ecosystem. So what we do is we separate out the kind of model that you want to train with the computational engine that you use to train it. So here, let's say we want to train a linear regression model, and then we want to use ordinary least squares to do it. So we would set the engine to be LM. But let's say during the course of EDA, we realize that there are many predictors compared to, maybe the number of observations we have. And so we are worried about overfitting. And so we decide we want to try a regularized model. We want to try a model that incorporates regularization. So we can use the fact that we learned that during EDA to decide what kind of model to use. And so in tidy models, we can fluently switch back and forth. We can fluently try both by switching out the engine in here. For other data sets, we might learn, or we might see during EDA that there's a lot of complex interaction between variables. And then we see that it's not likely that a linear model is going to do a good job. In fact, we're going to need a different model that's good at learning about nonlinear interactions, complex nonlinear behavior. Tree-based models like random forests are great at doing that and performing well when we have complex interactions. So that example of the trees in San Francisco is an example where I might do that, where there were more variables in that data set than just the spatial information. But just from looking at that initial map, you could see that there was complex relationships in the spatial information that was related to the outcome, who maintained the tree. And if you remember, that outcome was not continuous, but actually was a label or a categorical variable. And so we need to build a classification model and not a regression model. And again, this is something that we can fluently change in tidy models. So this might be just the most basic thing that we can start with as a modeling practitioner, like what kind of model are we going to use? But these are decisions that are made based on what we learn during EDA, often through what we learn using visualization. What kind of model is appropriate? Typically, the next thing we start to talk about and to learn that we need to learn during EDA is what kind of data pre-processing are we going to do? In tidy models, we capture data pre-processing and feature engineering in the concept of a recipe, of a pre-processing recipe that has steps. So you specify what variables you're going to use, and then you define the steps, as a recipe has steps, and then you prepare it using some training data, and then you can apply that to any other data set, like testing data or new data. So the specific feature engineering steps that we choose are typically chosen based on what we learn during EDA. So let's look at an example of that. So this is a data set of houses in Ames, Iowa. So there's a lot of information that we have about it, like how big they are, where they're located, and their last selling price. So this plot shows the sale price on the y-axis and the latitude on the x-axis. There's a big hole there, and that's where Iowa State University is. And then there's some unique and complex structure as you move across the city. And we have a number of options if we want to try to model that complex structure to be able to predict the price based on other information that we have about the houses. One of the options we have is to use splines. So we take the original variables, and then we build new features for modeling using the spline. So we build new spline features. The thing is, though, we have to decide how many spline terms to use. So 2 does not look like it captures the real structure very well to me. 5 looks better. I would believe 10. 10 looks pretty good to me. 20 seems okay, but I'm starting to feel a little skeptical. At 50, I no longer believe this. And at 100, this is just silly. So what's great about data visualization during the process of EDA is that we as machine learning practitioners, as modeling practitioners, can see and absorb this and then use it to make decisions. So those decisions are then captured in code. If you use tidy models, the code might look like this, with a feature engineering recipe that is defined with steps that transform and prepare the data to get it ready for modeling, whether that's dealing with lots of factor levels or creating indicator variables or setting those 10 spline terms as that last step does there. So whether it's engineering new features or choosing an appropriate model or understanding data quality, data visualization during EDA has a huge impact on what model practitioners do later on. So in a lot of ways, it's the foundation on which the rest of the model process is built. So it is often possible to estimate the best answer or value or option for choices like this using the data that you have. So for example, you can tune the number of spline terms using the data that we have. But it is nearly impossible to remove entirely the element of human judgment from these choices, or at least it's a bad idea. Machine learning algorithms are astounding. They're incredibly capable of learning patterns from large amounts of data. So vigorous adoption of data visualization during EDA is one of the safeguards that we have that's open to us against ending up in a situation where you have to ask yourself whether it was a good idea to just deep fry your data. All right, let's move on and let's talk now about model evaluation, the phase where we have trained and possibly tuned models, and we have predictions to compare to true values and can assess how our models are performing. And let's again ask this question, why are these plots built? So at a very high level, these plots are built to understand the models. And here we are, we're assessing model performance. So this is the point at which we as model practitioners have to reckon with questions about success and failure. We typically are trying out different kinds of models, comparing them, and we are looking across different multiple kinds of models that we have. The process of model evaluation also allows us to interrogate subgroups. And this is typically where discussions of model fairness come in. A lot of the current work on machine learning bias and fairness focuses on how models perform differently for different groups, maybe for differently legally protected classes that may not have been directly used as predictors in the models, but we may still see differences in performance in the output of the model, because it is possible that some of the things that are predictors are proxies for the things that are protected classes that we're interested in. Model evaluation is also concerned with understanding why a model is making the predictions it does, in looking at things like feature importance. For all of these kinds of questions, practitioners heavily use graphing, plotting, data visualization. Ultimately, for a lot of the same reasons that it is used during EDA, which are largely a lot of the same reasons that anyone ever uses data visualization. These plots are used to ask and answer these questions, to highlight relationships clearly that would be difficult to see otherwise. And they're used as supports and aids for making decisions that need to be made. At this point, these are decisions like, which model should I choose? Is this model fair enough? At the same time, there are some pretty unique things to note about plots used for model evaluation that I think are kind of interesting to note and point out. One of them is that many of the plots used for model evaluation involve graphical norms or idioms. So this plot shows how two metrics, performance metrics for a regularized regression model, a lasso regression model, change with the regularization penalty, like how regularized the model is. So someone who is familiar with these kinds of models can look at this plot and quickly recognize whether or not the model worked, whether it's a model that needed a lot of regularization or just a little bit. And looking at the R squared, how well, or in this case, how not well the model fit the data. So it's like a shorthand or an idiom that packs a lot of information for an experienced and familiar audience. This plot is similar. This is a receiver operator characteristic curve. It's 10 of them actually, for a model trained on that Palmer penguin data that we looked at the beginning of this talk. And it's a visual representation of how well a binary classification model is doing. So the more up in the left-hand corner these curves are, the better the model is doing. So the axes have the true positive rate and the false positive rate on them. And ideally, we want both of those to be great. We want the model to do a great job in both cases. So this is another example of a model evaluation visual idiom that is familiar to modeling practitioners that can be used to assess how a model is doing, to compare models, and so forth. So these kinds of visual idioms are a great fit for automatic plotting methods. When we talked about EDA, I highlighted the need for a really flexible plotting framework that can be used to create any kind of plot fluently. And we all need to adopt a grammar that lets you be able to create anything you want in a really flexible way. So a lot of model evaluation plots are the same every single time you make them. And practitioners can be better served using shortcuts that are built by tool builders like my team and me, because it can be a hassle to copy and paste the code for an ROC curve every single time. However, not all plots for model evaluation are these kind of standard idioms that are considered, normal or typical in the machine learning community. So this is also an evaluation plot. It's for a model predicting the class of a volcano. And each hexagon shows the percent of volcanoes that have been classified correctly within that little region of the Earth. So while knowing about some key automatic plotting methods are a useful part of the toolkit for modeling practitioners, still having that fluency in a flexible visualization system is very important, because there's not always going to be an automatic plotting method or one of these idioms to visualize performance in the way that you need to. So far, I've focused on model evaluation plots that show us how models are performing in terms of some metric like accuracy or RMSE. And like I mentioned, some work on fairness falls into that bucket, but like looking at differences in groups. Model evaluation activities also encompass model explanation. And visualization is also a key tool for explaining models. So model explanations fall into two main categories. The first are global explanations. This is where we evaluate what features are important in a model's predictions overall. So this plot is from the San Francisco trees again, and the length of the bars here correspond to how important that feature is in predicting whether the tree is maintained by the Department of Public Works or not for a random forest model. So whether it's a private caretaker or not is, the most important. And then after that, it's longitude and excuse me, longitude and latitude. So that spatial information is, is quite important in these predictions in terms of, does the Department of Public Works take care of any individual tree? So these are global measures of importance for the model overall. The other kind of model explanations are at the individual observation level. This is also called local feature importance. So there's multiple ways to do this. This particular plot shows an example of a Shapley additive explanation for a passenger on the Titanic, and a model predicting whether or not he individually would survive, where the Shapley value is the average contribution of a feature to the prediction in different combinations or coalitions for the model. So the box plots show the distributions of the values in different coalitions, and the bars show the average contributions, but just for that person, not for the model overall. So these are used for models that have where we don't have where it can be difficult to get global feature importance. So for both global and observation level model explanations, plots like these are used by the creators of the machine learning systems to evaluate and understand them. And at this stage of the modeling process, we're again at a point of important human decision, and model explanation together with model evaluation can be used to make choices about what models are going to be used. So through this whole process, this whole exploration of data visualization and the machine learning process, in this talk, I focused on plots made by system designers and operators for themselves as a tool to make better modeling choices. So think of these as plots made by practitioners for practitioners. Often discussions of data visualization center its function as a communication tool, and of course it 100% is. But we can also explore some of its other functions, like its ability to be used by system designers to understand the system more fully as they are designing and building it. Parts of the machine learning community recently have been exploring what are called participatory approaches to machine learning, where the system designers purposefully partner with individuals who are impacted by the system as they're designing it, like partnering with the users of the system as they're designing it. And I think this is going to be really interesting to watch, because that kind of practice and approach of the purposeful partnering is going to have to impact choices throughout the model process, including what kind of plots we make and who do we consider the audience. And it may change the answer to this question: who are these plots for? What I don't think it's going to change is the main purpose of any given data visualization made during the machine learning process. Some plots are created to help us understand the data that we start with, the input for the models that we create. So investing in data visualization to understand the data is like laying a strong foundation. Some plots are created to help us understand the models, the output, and careful visualization practices in model evaluation sets us up for success in models that are as accurate, as appropriate, and as reliable as possible. And with that, I will say thank you so much to this user group for having me. I want to make sure to thank my teammates on the Tidy Models team, as well as the folks who organize the Tidy Tuesday project. Tidy Tuesday is a weekly social data project that most of the data sets that I shared today are from. So I will see if we have any time for questions and whatnot as we start to wrap up.
Okay, Joyce has a question. Rich, can you unmute her?
Hello.
Hi, how are you?
Hi, good. Thank you. That was a fantastic talk. I love the connection between EDA and modeling. I wanted to ask about how to kind of foster that relationship. I'm in education, and I find that the work I teach EDA, but they're very separate worlds, and it's not always easy to get people on the modeling side to use visualization. And maybe vice versa. I mean, the textbooks are separate. So
Yeah.
I was wondering if you have that experience in industry, and if you have any thoughts. I mean, the things our studio is doing certainly contribute to the connecting those two domains. But just any comments you have on that would be really interesting.
Yeah, you like Joyce really raises a good point that like the textbooks are different. Often when you do a tutorial, the modeling tutorial doesn't start with EDA. The modeling tutorial starts with like this cleaned data set that you take as if a gift from heaven, that like it's ready to go. And so I think this is a really important issue that's being raised. I think one thing I would love to see is when EDA is being uh, taught, if you're in a specifically explicitly teaching environment, or in a more casual or informal mentoring relationship, when you're like seeing people do EDA or you're communicating about EDA topics, is to be a little more explicit about why are we doing EDA. Typically, I mean, so typically we're doing EDA to learn things and to often set up for some longer term goal. Like we're either that this is we're learning things now, and then we are setting up for the ability to do larger things. And that if we don't do this now, we undercut our ability to take any further steps. I also think I'm a really big proponent that people who teach machine learning and modeling and don't acknowledge how important a real understanding of your data is, are doing a disservice. So I'm working with my coworker, and the leader of my team, Max. We're working on a new book about modeling right now, and one of the things we wanted to do is make sure that in the beginning of that we talk about EDA and show at least a little bit of it. And so I think that on both sides, either like drawing the connection that like part of the reason you're doing this is to set yourself up for further tasks, and then on the modeling side, um do more acknowledgement that like the reason a modeling tutorial can start bam with like time to split your data, into training and testing, is because it is already clean and the person already knows what's in it. So that's a great question.
There's a question in chat from Adam Finkel, which is, human beings are frail and fallible, yet we have created tools of incredible precision. How can we do the same for data science and machine learning?
So a big part of the design goals of the software that I work on is acknowledging acknowledging that that the models are able to learn patterns with incredible, like are able to really learn incredible patterns from large amounts of data. And one of the biggest needs, I think, in data science and machine learning now is software that empowers more real world practitioners to engage with good statistical practice, so that that when we try to use really powerful machine learning algorithms, whether it's a random forest or something, with even more able to learn these patterns, that we have a toolkit that protects us from making from making those frail and fallible decisions. So some of the things that that exist in the Tidy Models toolkit that I would point to are very explicit teaching and software design around guidelines around kind of what we like to call your data budget or data spending, in terms of like, how is resampling done, and how do you use resampling to protect against overfitting? How do you understand that you are protecting against data leakage? The design of how you saw that lovely illustration about recipes for data pre-processing, and the like a lot of the design decisions that have gone into data and into recipes are to protect against those frail, fallible decisions that are so easy to fall into around, say, data leakage during data pre-processing. So I think that acknowledgement of how powerful many of these machine learning algorithms are, and careful design around the human-facing layer of how we as practitioners interact with them is something I care about a ton, and one of our real goals that we have. All right, and I think there's someone has their hand raised.
Yes, I do.
Okay.
Hi, Julia.
Hi.
Hi. My name's Mark Perman, and I want to ask a question that's probably a little bit, it's poorly formed, but I think I'll figure it out as I talk it through. It was inspired by two things. The first is you mentioning, when you started your talk, you sort of said, oh, it's very interesting to talk to a group that is focused specifically on data visualization, as distinct from, say, doing data science or data analytics. And then also building on that first question about kind of, how to, sort of marrying visualization with modeling.
If I can't, because I can't name the documents.
Sorry, can you hear me?
Yes, sure can. I think
Okay,
somebody was just unmuted for a moment.
Yeah, no problem. So my question is, do you think, and I recognize you may not, kind of have a real answer on this, but what's your opinion? And also you're building tools. Do you think that, improving the kind of the use of visualization in modeling will come more from modelers, people whose primary responsibility is modeling, sort of learning more about data visualization and picking up new tools like your team is building? Or do you think, it might come from people who are more data visualization specialists, which is like someone like myself, kind of partnering with modelers and kind of doing the heavy lifting on the visualization so that they can focus on the modeling. Does that make sense?
Yeah. One thing that this brings to my mind that I would love to know more about is what I talked about, this idea of like a visual idiom that people use in model evaluation, and the ones that I showed were ones that people generally have good experiences with, and that people are like, oh yeah, I'm using this because it's a norm and used widely, and because people tend to just as like a heuristic, people have like, oh yeah, I found that useful, and so did my coworker, and we're continuing to use it. And the statistics is kind of full of things that didn't work. And one, I was talking to one of my coworkers about this, and Mina Sedinkaya Rendell, and she pointed this out to me. I was like, oh, that's so interesting. that there's this research about the QQ plot, you know, you do a linear model and then you do like the QQ plot, and how it's basically like useless. It's another model evaluation plot, but the idea, like what the research showed, like just briefly, is that if your model is fine, it shows you it's fine, and if it shows you it's not fine, it's just entirely unactionable. Like there, you're just like, oh no, and then you're just like, oh no, you know, there's just like nothing to do with it. And
Right.
one thing I think that the machine learning and modeling, like especially practitioner community, like everyday practitioner community, really needs is like a little more like rigorous data visualization research in terms of why like why and what, at least just like what is good practice, like which one of these things are working and why, especially maybe on that evaluation end. I think on the EDA end, there's a lot of just overlapping research, like knowledge already, because the reason it works is the same reason you know, EDA for data science in general works, right? But so what your question really makes me think of is that there's still so much that is unanswered, and because, you know, machine learning as a field of practice, as like a, hey, look, there's just people doing it at your regular company,
Right.
it is so new
Yeah.
that people are really just finding their way.
Yeah.
And so that people who do data visualization as their field have there's just a lot of open questions still in terms
Yeah.
of like what um are there better options?
Yeah.
Yeah. That's what comes to mind when I ask that, when you ask that question.
Great. No, that makes a lot of sense. Thank you very much.
Yeah.
So Julia, there's a question in chat from Daniel Grinnell, and he wrote that he's in a noisy environment. So I'm going to read it unless you want to read it.
I'm seeing this. Okay, so this person, I'll read it for anybody who is just listening. So Daniel wanted to use Shapley values globally by averaging the local Shapley values, and then had difficulty communicating that. And says, was I on a fool's errand? And boy, I've been on plenty of fool's errands myself over. So I definitely feel you on that. I would have to do a little bit of research to feel more confident, to be 100% confident, but I am pretty sure. So take this with a grain of salt, but I don't think for global importance you want to be averaging over all the local values. I'm pretty sure you don't want to be doing that. So if you have a model that you want a global answer for, and that you and it's not something that is like a tree-based model or a linear model or something that you just get feature importance out fairly straightforward, in a fairly straightforward way. There are things you can do that are not averaging local values. So some of those things are like partial dependence plots. There's these things called ICE plots, and I find them, quite like and again, these are almost all visualization methods, and I find them I don't want to say transparent, but good communication tools. You know, if you're for either good ways to understand the model yourself, or to communicate to a team about what the model is doing. So I think I would point you in a different direction to something that is studied a little bit in more detail. If you're an R user, I would point you towards the VIP package. It stands for like VIP, variable importance. And it has methods for, the things where variable importance falls out quite straightforwardly, like a trees, but it also has ways to get for any model. If you can predict, it can give you things like partial dependence plots, which can might be a better, more straightforward approach to that problem. Has a little more let's say a little more might be on a little more firm foundation. No, I'm sure this does the same thing in Python. So I think look for something like partial dependence plots, ICE plots. Yeah, so what you're looking for is model agnostic variable importance. That's what you're looking for, model agnostic variable importance. I'm sure the same thing exists for Python. I'm sure it's out there. Great. Anybody else have any questions? I know we're at the hour. Great. Well, I want to thank again the organizers, and I want to thank you for your wonderful questions. It was a delight to be here with you all. Thank you so much for having me.